Hello everyone and welcome to the Regents Chemistry Review Series. In this video, we're going to talk about matter and changes. So why do we need to talk about matter? Because chemistry is the study of matter. So matter is anything out there that has mass and it occupies some space, meaning it has some volume. So when it comes to classifying matter, we can first of all classify matter based on its composition, meaning what is it made of. So based on composition, matter can be classified into either pure substances or mixtures. So pure substances are composed of chemically combined atoms. Sometimes we can also just have atoms not combined with each other. So those type of pure substances are called elements, and the substances where we do have atoms combined are compounds. So elements can be either just one atom of that substance. So those are called monoatomic elements. So there are so many elements, or maybe we should say most elements in nature occur as monoatomic elements, meaning as one atoms. However, we do have some atoms out there that do exist as diatomic. So in nature, we have two atoms of those elements combined. For example, your oxygen gas. So oxygen always exists as diatomic. We have two oxygen atoms chemically combined. If we have atoms of different elements combined with each other, then that type of matter or those type of pure substances are called compounds. So these atoms are chemically combined to each other, meaning they are bonded to each other. So if we want to separate them, we're going to have to break the bonds, and that normally happens as a result of a chemical reaction. So we can sometimes, you might hear this word a lot, a binary compound. So binary compound is when we only have two atoms in a compound. For example, sodium chloride, NaCl, that's your table salt. That is an example of a binary compound because you have sodium and chlorine, only two atoms. However, if you're looking at a compound like potassium permanganate, that one has potassium, it has manganese, and it has oxygen. The chemical formula is KMNO4. So that will not be a binary compound. So besides pure substances, matter can also be classified as mixtures. The thing that makes mixtures different from pure substances is that in mixtures we have physically combined pure substances, meaning if you want to separate them in lab, we have very common lab techniques that we can use to separate the mixtures from each other, and once we separate them, they are going to be in their original condition again, which is not the case with chemical composition, because when you have oxygen and hydrogen combine to make water, which is H2O, if you break the bonds and you separate the hydrogen and oxygen, they are not going to become hydrogen gas and oxygen gas. So the three things are very different from each other. So physical combination and physical separation is very different. For example, if you're combining salt and water, you can evaporate the water to just get salt. So now the water and the salt are separate from each other and they are back in the state that they started from. So there can be two types of mixtures. We can either have homogeneous mixture or we can have a heterogeneous mixture. So homogeneous mixture is when we combine two things and they are completely mixed with each other. For example, once again, your salt solution. So salt, if you try to dissolve that in water, is completely dissolved in water. So when you look at the mixture, it looks the same everywhere. So any type of aqueous substance, any type of aqueous solution besides your salt and water is a very good example of a homogeneous mixture. Aqueous substance means you take any substance and you dissolve that in water and it's completely dissolved. That will be an aqueous substance. So the AQ that you see in the parentheses there, that is the symbol that we use to represent an aqueous solution. We'll see what that looks like in a chemical formula in a little bit. So heterogeneous mixture on the other side is when you have different layers or different forms in your mixture. So this is when your substances in the mixture are not completely dissolved. So think about a sand and water mixture. If you put sand in water, there might be a very small amount of sand that will be dissolved in water, but for the most part, sand does not dissolve in water. So you're going to see those sand particles separate from the water in that mixture. So that type of mixture is a heterogeneous mixture. So then, what if we want to go ahead and separate the mixtures? How does that work? So there are different techniques that we can use in the lab to separate the mixtures. Please remember that you have to memorize all of them. So the first technique that we can use is magnetism. So magnetism can be used to separate something based on magnetic activity. For example, you have iron dissolved in sand. So you can just take a magnet, the iron will be attracted to the magnet, and that's how we can separate all of the iron from your sand. The second technique that we can use to separate mixtures is decantation. So if you have sand and water mixture and you want to separate them, you can just pour off the water from the top, and that is going to be they are going to be separate from each other. We can also use filtration for a mixture like that, like for a sand and water mixture. So in that case, you would mix together the sand and the water, and then you're going to pour the mixture on top of the filter paper, and then your mixture, your sand is going to stay on the filter paper. A very, very important thing to remember about filtration, and this is going to show up in some questions. There's like a 99% chance for a question on filtration. Is that filtration is based on the difference in particle size. What we mean by that is if we, I'm trying to find a highlighter here, which I cannot find. All right, that's okay. So what we mean by this is the reason why, the way you can get the questions is why was sand able to stay on the filter paper? So your answer is that the sand particles are larger than, let's say, the pores in the filter paper. So filtration really depends on the particle size. If you have bigger particles, they're going to stay on the filter paper because they're not able to pass through the filter paper. All right, and then the next technique is crystallization. And some other words that you can use for crystallization are evaporation or boiling. So this is something that can be used for a solution that is homogeneous. For example, let's think about the salt and water mixture. So because salt and water are completely dissolved, you can boil off the water, and then you're going to be left with salt in your beaker or like whatever instrument you are using. Equipment, sorry. So crystallization is a good technique to separate homogeneous mixtures of a solid and a liquid. And then we can, I don't know why both of them showed up together, but that's fine. So the next technique is distillation. This is something that we can use to separate two liquids that are completely dissolved. For example, think about maybe alcohol and water. They dissolve completely. So another very, very important thing that is very likely to show up on the exam is what does distillation depend on? So I wanted to highlight this thing. So distillation is based on the difference in the boiling point. So remember that alcohol and water, they both have different boiling points. So what we do is we start boiling the mixture, and because alcohols have a lower boiling point, meaning they're going to boil off first, so when they boil off, you can go ahead and collect the alcohol in this flask that you see, and then in this flask over here, the one that we started with, we are now only left with water. So water is not going to boil off with alcohol because, again, water has a higher boiling point, so it's going to stay in that flask for a longer period of time. And then last technique that you need to be aware of is chromatography. So chromatography depends on the difference in the solubility or polarity. So what we normally do is that we put like a small spot. So the X is your sample. So we put like a small spot of your sample on the chromatography paper, and then we put the chromatography paper inside the solvent. Now there are different substances in our sample. So we have substance A, B, C, and D. And then all of them have different solubility in the solvent that we are using. So some of them are very soluble in that solvent, and some of them are not so soluble in that solvent. So what's going to happen is that the substance in our mixture, which is less soluble, is going to be separated from the mixture first. So it's going to show up somewhere at the bottom of your chromatography strip. And the ones that are more soluble in the solvent are going to stay in the solution for a longer period of time. So they are going to be somewhere at the top of your chromatography strip when you observe your strip after chromatography. Alrighty, so these are the different ways in which we can separate the mixtures. Once again, please make sure that you memorize all of them. The next thing that we want to know about matter is something called the particle diagrams. So we can be given a particle diagram that looks something like this. Now, a very, very important thing to remember about particle diagrams is that when you see this one dot, this represents an atom. So in this case, we are observing the same type of atom everywhere in the particle diagram. So we have that completely filled circle everywhere in the diagram. What this tells us is that we have the same type of atom in this diagram. So that means we are looking at a particle diagram of an element. The reason why we know that this is an element is because this atom is separate. It's a lonely atom. It's a monoatomic thing. We can also get a particle diagram like this. What we notice in this case is that we have this atom, let's call that atom number 1, which is completely filled, and then we see 2 other atoms which are the same type. So these represent atom number 2. We know that both of them represent the same element because they look the same. They are not filled. And then we see that these 2 atoms are combined to each other. They are joined to each other, meaning they are bonded. So they are chemically combined. And then if you notice, we have the same situation going on everywhere in the particle diagram. Whenever you have the atoms of 2 different elements chemically combined to each other, that means we are looking at a compound. And then because, as you can see, we have the same type of compound everywhere else in the diagram, so that means we are looking at the particle diagram of a compound. So we see a fixed ratio of elements in the compounds, and this is a very, very important thing to remember. You can say that this is also a part of the definition of a compound, that we have atoms of different elements combined in a fixed ratio. So let's look at another type of particle diagram that you can get. So in this case, we notice that this one is one type of compound, so we can say that this is compound number 1. And then we see another type of compound, so let's call that compound number 2. And then we kind of see these 2 types of compounds everywhere else in the diagram. So because compounds are pure substances, and we see different types of pure substances in this diagram, and as you can see, these 2 compounds are separated from each other, meaning they are not like the atoms in the compound which are actually like next to each other, meaning they are bonded. These 2 compounds are not bonded to each other. They are in the same diagram, but they are not joined to each other. So that means we are looking at a physical combination. So this one is a physical combination. So that represents the particle diagram of a mixture, and more specifically, it's a mixture of 2 different compounds. And there is no fixed ratio for a mixture, because as of this moment, if you look at your diagram, you see that we have 4 particles of compound 1, and we have like about 4 particles of compound 2. However, if I give you like 3 and 3, or if I give you like 3 and 4 or something, it's still going to remain the mixture of 2 different compounds. So mixtures have no fixed ratio. Alrighty, so next up, let's talk about the classification of matter based on the physical states. So this is the second way in which we can classify matter. So in terms of physical state, matter can be in the solid phase or liquid phase or a gas phase. And here, if you look at their particle diagrams, so these are the particle diagrams, which can also give us some information about the arrangement of the particles, and you actually get a lot of questions about particle arrangement. All you have to say in your answers for particle arrangement is how close the particles are to each other. So in case of solids, particles are packed together and they are very organized. For the liquids, particles are not so organized, and they do have some space between them. In case of gases, particles have a lot of space between them, and they are absolutely not organized. They are like all over the place. So because of this particle arrangement, if you talk about the shape of solids, liquids, and gases, solids have a fixed shape, again, because particles are organized, they are packed together. Liquids have no fixed shape because particles can still move around, and then gases again have no fixed shape because particles can move around. For volume, solids have a fixed volume, once again because particles are packed together, so they occupy a specific amount of space. So just so everyone remembers, volume means the amount of space occupied by the substance. In case of your liquids, the particles do have a fixed volume, because if you know that you have 5 milliliters of water, you know how much space that water is occupying, right? However, in case of gases, there is no fixed volume because there's so much space between the particles that it's very hard to say, even if we know that we have our gas in 5 milliliters, not 5 milliliters, let's say, maybe like a 5 centimeter cubed container. That's the volume of the container, not of the gas, because gas particles in that container are still very far apart from each other, so they're not occupying the entire space in that container. All right, so then if we talk about the distance between the particles, as we mentioned earlier, solids have very little to no space, liquids have some sort of space, and gases have a lot of space between the particles. In terms of particle motion, because solids do not have any space to move, so the only type of movement that can happen for solid particles is vibration. In case of liquids, particles do have some freedom to move around. In case of gases, however, because there's so much space, particles move a lot. And at the same time, very important to remember that gas particles move at a very, very high speed. Primarily because they have a lot of space to move. So they can move at a very high speed. Compressibility, meaning can we bring the particles closer together? So in case of solids, no, because they're already, they're as close as they possibly can be. So there's solids are not compressible. Liquids do have some sort of compressibility. We might be able to bring them maybe a little closer. Gases, however, are highly compressible because, again, a lot of space, so we can bring the particles closer together. Entropy means how much randomness or disorder do we have between the particles. So solids have very, very low entropy because there's literally no randomness. They're very organized. Liquids have some sort of entropy, and gases have the highest entropy out of the three states of matter. Alrighty, so the next thing that we're going to look at is the chemical formulas of the different types of matter. So chemical formula, first of all, we do want to remember the definition. They represent the number of atoms of each element that we have in a substance. So let's look at some examples. In the first one, we have mercury in the liquid form. So the L right there, that represents the liquid form. And because for mercury, we don't see any coefficient. So if we see a number over here, this number represents a coefficient. And if let's say I want to say that I have 2 atoms of mercury, I would put a 2 as the coefficient. However, if I want to say that I have 2 atoms of helium, I'm going to put the 2 as a subscript instead of as a coefficient, and that is because helium is a diatomic element. Okay, so the elements that are diatomic, we can put the we can, if you want to say that we have 2 atoms of this element, we can put the 2 as a subscript, because this 2 represents that those 2 atoms of helium are bonded to each other. But if you put the 2 as a coefficient, that means we have 2 atoms of mercury which are not necessarily bonded to each other. They might be next to each other but not bonded. Alrighty, so in this case we have 1 atom of mercury, and it's in the liquid form. For helium, once again we have 1 atom, it's in the gas form. We know that because of this little g at the bottom. We have 1 atom of sodium in the next one, and it's in the solid form. And then in the next one we now see that subscript of 2, so that means we have 2 atoms of oxygen, and this one is in the aqueous phase, meaning we have this oxygen gas dissolved in water. So oxygen dissolved in water. So let's look at the chemical formula of a compound. So it's going to look like this, and this is a complicated one because you see some subscripts inside the parentheses and some subscripts outside the parentheses. So if we count the number of elements, in this case we've got 1, 2, 3 elements. If you want to count how many atoms of each element we have, then we are going to have 2 atoms of aluminum because we have a subscript of 2 there. For sulfur, we don't see any subscript inside. However, we do see this subscript outside for sulfur. So that means we have 3 sulfur atoms. And then for oxygen, we see 2 subscripts, 1 inside the parentheses, 1 outside the parentheses. So we're going to multiply both of them. So that means we have 12 oxygens. Alright, so this is what your chemical formula for compounds is going to look like, and then that little s at the bottom means that this thing is in the solid form, a solid phase. Alright, so last thing that we want to discuss in this unit is the difference between physical and chemical. So physical properties are the properties that can be changed without changing the chemical composition of a substance. Meaning, if I take solid water and if I convert that to the liquid water, it still has the same chemical composition. Solid water has the chemical formula of H2O. Liquid water also has the chemical formula of H2O. So chemical properties, on the other hand, cannot be changed without changing the chemical composition. So this normally involves the reactivity or flammability. For example, if you take a piece of paper and you burn that piece of paper, it's not paper anymore. So the chemical composition changed. So physical change then would be the change that does not change the chemical composition. So as I mentioned, phase changes are the most common examples of physical changes. So here we can see what it looks like in terms of particle diagram. So on the reactant side, we see that the particles are very close to each other, so that represents maybe like a solid phase. And then on the product side, the particles seem very far from each other, so that could be the gas phase. Alright, and then in this case it looks like we are only representing an element because we see 1 atom in a particle. So chemical composition, however, in general is not changing, because on the reactant side we have that 1 particle, or all of the particles just together. In the product side they are a little spaced out, but it's still like the atoms still look the same. In case of chemical change, however, because chemical composition does change, here's what your here's what your particle diagram is going to look like. So these, let's say these type of particles where you have the unfilled atoms, 2 atoms together, they represent H2 gas, hydrogen gas, and then the ones that are filled could represent the oxygen gas. So these are 2 different types of substances. When they combine, on the product side, they make water. Now, the thing to remember here is that all 3 of them have different formulas. So H2, O2, and H2O. All 3 of them are 3 different types of substances. Okay, so that's why we say that whenever a chemical change or a chemical reaction occurs, chemical composition changes. Whatever we start with, we do not end up with the same thing. The chemical formula changes. So that wraps up Unit 1. I hope you all got all of the information that you need for this unit.